Okay, and as I said, let's be first also continue here for the recording. Great. Yeah, so please ask questions also in between if you want. I mean, I wouldn't mind. It's better to ask a question than to be lost. And yeah, so most of you maybe are even more experts in machine learning here than I am, right? I am by heart a mathematician. So I will start slowly with the definition of neural networks for me. And so the beginning might be a little bit boring for you, but stick around. It's going to be challenging enough in the end, I think. So otherwise, let me start. So I will only use feed-forward neural networks for the presentation today. So that is a network. Such a network eats an input vector and then produces an output vector. And for that, it uses a bunch of nodes, which are grouped into several layers. And in my setting, I want every node in one layer to be connected to every node in the next layer. And so this is, I'm working with fully connected networks at the beginning of the talk. And I have a weight, possible unknown weight on each of these edges. So I just marked here 3 of them. So in total, I have an input vector x, output vector y, and weight vector w. And all of a sudden together, you know, this gives us a continuous mapping. So a neural network is somehow really just some very special case of a continuous parameterized map from the weight space and the input space to the output space. And somehow the key player, since I'm a geometer and I'm interested in geometric structures in applied questions, is for me what many people call the neuromanifold. Sometimes people also call it just the function space. And it's simply the set of functions that the neural network can parameterize. And so for a fixed weight vector w, the neural network gives us a fixed function from input to output space. And if I now vary all these weights w, then I get a family of such functions, and that's the neuromanifold. Okay, so let us do some super easy observations at the beginning about this object. First of all, in most settings, this continuous mapping phi is a piecewise smooth function. And that would mean that the neuromanifold is not really a manifold, but a manifold with singularities. So it deserves this name. And interestingly, as you see here, somehow my pen does a funny thing. So as you see here, the neuromanifold is contained in an infinite dimensional space, yeah, of all continuous functions from input to output space. But since it is parameterized by the different weight vectors, itself is a finite dimensional manifold, which makes its study much easier, of course. Okay, so in these 2 works that I kind of wanted to talk about today, we focus on linear networks first as like the running example. And as you know, these are, of course, in practice not very relevant, but they're like a good start case to really have a thorough study on the theoretical side of neural networks. So I will start with these fully connected linear networks, and then at the end say something about what happens if you do convolutional networks, but that are still linear. So as most of you know, I think, a linear network is just when the nodes really don't have any activation function on them. So that means that the continuous mapping is really just a bunch of matrix multiplications, and then you get a big matrix at the end, and then you multiply that with your input vector. So a linear network, our continuous map phi, eats a bunch of matrices w and an input vector x and multiplies everything together. Okay, so this is just to double check, like, oh, what are these dimensions of these involved spaces here? And what is the neuromanifold, right? That is now the interesting key player if you want to study fully connected linear networks and you're a geometry person. So the neuromanifold of the linear network is, in this case, all matrices that are bounded in rank. Right, so this matrix that I have here, this matrix M, is really the product of all of these matrices, so to say. The neuromanifold is all matrices that you can factorize in that product. That would be the formal statement. Because the functions that the linear networks parameterize are just linear functions that multiply the matrix M with the vector X. And then it's an easy exercise, if you know linear algebra, that if I ask the question, which matrices M can I factorize in the way I wanted to factorize, where you want to involve all of these dimensions, then you exactly get the set of all matrices whose rank is at most this minimum. And again, if that doesn't make sense, you're very welcome to interrupt me, and we can clarify. But I hope really that this example is clear. Okay, so the neuromanifold is a set of rank-bounded matrices. And since this is such a long expression, I will just call this rank R, the maximal possible rank. And now there are somehow two fundamentally different cases. Let me first tell you these cases and then tell you why I care so much about these two different cases. So the first is if R is really the minimum of either the input or the output dimension. So that would be, let me try to draw something. Like if I have a network, I sketch the layers, yeah? So if these are different layers of the neural network, and I have only like that the small layers are the input or the output layer, that would be this case 1. Does that make sense? That would just mean that the rank is not bounded at all, right? Because I'm dealing with dh times d0 matrices, and so clearly the rank is bounded by that. So this is the very easy case where the neuromanifold is just a vector space. And this is what I will call in this talk a filling architecture. Why? I will say in a second. Geometrically, maybe the more interesting case happens, though, when this rank is smaller than either the size of the input or the output layer. So that would be something, for instance, like an autoencoder, right? This would be like a network that maybe looks like this. Yeah, where it says 4 layers in this example, and the tiny one is like in the middle. And so this is what I will call a non-filling architecture. And the neuromanifold is not a vector space anymore. This is now really rank-bounded matrices. And in algebraic geometry, these are classically studied for hundreds of years, and we often call them determinantal varieties. So why do I care about really distinguishing these two cases? So in the machine learning literature, these are often distinguished, like we're not the first one doing this, but people do not often always say like somehow the geometric meaning. I think so what we try to achieve with our line of work is to not just prove certain statements, but really explain why they are true. I mean, this sounds like it's the same thing, but it's not really the same thing. Like I can understand and follow a proof and see, yeah, the proof is correct, the statement must be correct, but I can also understand it maybe in different ways. And then maybe many assumptions people make become clearer if you really understand why you actually need certain assumptions at certain places. So the first case we call the filling architecture, where the neuromanifold is just a vector space. And the second case is what we call non-filling architecture, Here, we're dealing with an algebraic variety, which is neither a convex set nor even a smooth manifold. So this is already, in this easiest possible setting of neural networks, we're dealing with a non-smooth manifold. Maybe a quiz question. I guess many people know what is actually the singular locus of the neuromanifold. It's all matrices that have even smaller rank. So you have some sort of nice rank stratification in this geometric object. Okay, so that was my startup setting. Now, what do we want to do with it? So one common thing that we want to do in machine learning is we want to optimize a loss function on our neural network. And so these loss functions are of the form, typically, in that they actually come in some sort of naturally factorized form. So the loss function I call here capital L, and it factors as follows. So first, for each weight vector, I use the parameterization map that I write here mu, that actually would then fix the network and thus the function it represents. And then I have like this functional which I write small l, which I want to evaluate. We're also going to see examples of this soon. Don't worry about that. So this small l is just any sort of functional that has to be defined on some subset of the continuous function that contains the neural manifold. So it's a very, very general setting. And these functions, this capital L can or is typically very, very crazy. I really enjoyed reading this article in 2018 where they gave these beautiful visualizations of how crazy somehow the loss landscape looks. And so this is somehow where we want to optimize. And there's, in general, I think, I like to think of the theoretical papers in machine learning on this loss landscape questions. They're often of two flavors. Either people want to study how the loss landscapes look, like its static properties. And the second thing you might want to do is really do a dynamic approach, where you're not just interested in how it looks, but how, for instance, gradient descent or any other algorithm would move in it. And so for the beginning of this talk, let me stick with the static idea. So I really want to understand how this loss landscape looks in some sense. And again, please feel free to interrupt me if you have a question at any point. So a very first observation is the following, that whenever I have a critical point on my neuromanifold, right? So like I had for like some, well, for some weight vector, this is actually like a fixed neural network. There's actually a function here in this neuromanifold. And whenever I have a critical point of the functional small l, then of course everything in the pre-image, like whenever I take this phi and consider the whole pre-image under this parameterization map mu, this has to be critical points of the loss function. And so typically this set, this pre-image, is a large set. It's often infinitely many points in practical situations, right? Because typically we're dealing with the fact that our neural networks are over-parameterized, right? So that's the same thing. So yeah, so for every actual function phi, we typically have very, very many weights that give us that function. And when phi was a critical point, then all of these weights are a critical point. And so a good first question, I think, that one can try to ask for many different architectures is, how does this set look? And so this is like a question I want to study now on the next slide. So how does this pre-image look, mu inverse of phi? And this is interesting because think, for instance, of imagine I could somehow magically tell you the global minimum on the neuromanifold. This would be the perfect function phi to have. Okay, but now I am doing gradient descent on the weight space, right? On the set of all weights. So I will hopefully find possibly a weight that corresponds to this global minimum. However, there is infinitely many weights. So it might be that all of these weights have the same, well, obviously they have the same loss value, but they might have other different properties, right? They might behave better when it comes to numerical stability, or different weights, although they have the same loss, might lead to better generalization than others, and things like this. Or they might be more stable against adversarial attacks. I mean, the loss value is not the only optimization parameter one might want to have. And so one thing I was discussing with several people for a while is like one could, for instance, have this dream of finding a very good weight vector and then be able to move in the space of weight vectors to other weight vectors that give the same loss, and be able to move in them and find one that works better for other reasons. So that's why I really care about this set, for instance. Let us do this example. Okay, this is like a homework exercise, but maybe a very complicated homework exercise. What happens if you want to answer this question for linear networks? So here is again the recap, what linear networks do. I have the function mu that multiplies matrices together, and then the functional small l evaluates on this common product M and outputs a number. So here is the answer on a topological perspective. And we see this set already becomes quite complicated, even for these super easy networks. So when M is a matrix in the neuromanifold, which has the maximal possible rank, then this pre-image set, mu inverse of M, I cannot move typically from every weight to any other weight because it has 2 to the b path connected components. So this is already some interesting information. And so what is this number b? So I gave you the definition, but I can maybe draw a tiny picture to make it clearer. So b just counts how often a layer of size r, like how many layers in the network have width r. Okay, so if I'm trying to draw an example, like in this example, if you imagine that the 2 dashes in the middle have like the same width, then b would be 2. And this number b never counts the input nor the output layer. As like a okay. And then, interestingly though, if you have a matrix whose rank is not as large as possible, and it depends, I think, a lot on your application, what is the more common occurrence, then this set is actually a path-connected set, but yet very complicated. As I can describe it a little bit better, but then it gets technical, so I didn't want to talk too much about it. But I'm saying this is like an interesting question, I think, also for experimental studies, to do this sort of pre-image question for other architectures and other activation functions and not just linear networks. Any questions so far? Everything's good? Then let me go on. So now I want to kind of spend most of my remaining time discussing this bold sentence. So you often hear, I think, in many talks and conferences that linear networks are easy and they're like well understood and we don't really have to do this possibly anymore. And like they often have no bad minima, like every local minimum is global. And the question is, though, like what does often mean? And we do have a good understanding of this. I think of this specific question, it is indeed well studied. And I want to stress again a little bit why this sentence might be true and why it might not be true, and really focus on the geometric meaning and not just on giving some sort of formal proofs. So one thing, like this proposition, I think is not very difficult to prove, but still I think in some sense deserves to be like a theorem, because I think the insight is quite important. What is true for linear networks is that the loss function, capital L, has no bad minima if and only if this functional small l on the neuromanifold has no bad minima. And that this is an only if is a really important and remarkable property for linear networks, which is, for instance, if you just, fully connected linear networks. As soon as you, for instance, go to convolutional linear networks, this theorem is not going to be true anymore. But for fully connected linear networks, it really is. And why I think is it so important? Because in the actual machine learning world, when we run our experiments, then we will always work, of course, on the parameter space over here. And I want to know if it's bad minima. But if I am a theoretical mathematician, then this seems to be the much harder problem to study. But it seems to be much easier to study only this problem. Like I have some nice, beautiful neuromanifold that we understand very well in this case. And it's an optimization problem on the space. And so answering the question either on the neuromanifold or on the parameter space is equivalent in this case. And if you have this, this proposition, then from there follow immediately, more or less immediately, very celebrated results in the literature on linear networks. So for instance, there is this statement from Lauren and von Brecht, and it kind of reads as follows, that when I'm working in this case, where I'm in the filling architecture, like they don't write it with the filling architecture, but as I said, that's what I want to say, then they say that all local minima are global. And this is now an easy corollary from the proposition above, right? Because, let me remind you, what does this filling architecture mean? It means that our neuromanifold was just the whole vector space. So the neuromanifold is just a vector space. And if I have a smooth, convex function on a vector space, then that one clearly just has a single local and thus global minimum. And because of this equivalence, this is now also true for the loss on the weight space. Again, if you have a question, you're already welcome to interrupt me. Yeah.
Sorry, I raised my hand.
I'm not sure if I see the. Yes,
no,
okay,
sorry,
yeah.
I should have interpreted. So a quick question, because I'm a bit confused for the pre-image. So when you talk about pre-image, I can see two pre-images. One is when you go from a point in the manifold back to the weighted space, and one is that you go from the loss, from the scalar loss, and then you go back to the weight space. So when we talk about the generalization and the stability, so stability I see as the pre-image. You can explore the stability of this this function, then you go from the preimage of a phi from the manifold back to the weight space. But when we talk about generalization, to me, you should go. It's not mu inverse. It should be like the whole L inverse as well as mu inverse. Is that correct, or?
I mean, I think it depends a little bit on your setting. I have not been very formal also when I said these things, right? I mean, so I was thinking of like a loss function that comes from some training data, and then of course you don't really know. Oh yeah, you're right. I think, right? Yes, because for generalization, yeah, you're right, because you get somehow the same function, of course, right? You would get the same function, and so it would do the same thing. Yeah, you're right there. Yeah.
Okay.
I mean, one thing that might though affect this. I mean, I'm wondering, for instance, if these stability against adversarial attacks or so, because if you choose different weights, right, and they're not really nice normalized or something, I mean, then you have maybe worse gradients on each, or like worse behavior, right, on each layer or something. Yeah, good points. Thanks for the correction. Yeah.
No, thank you. No, I was a bit confused because we talked about local minima now, and then I was trying to get on the same page. Okay, thank you.
Yeah, thanks. Okay. And again, more questions, please feel free to interrupt. I don't think I will look out for raised hands. I think that's gonna be a problem with my mental capabilities while giving a talk on 2 devices. So, okay. Yes, so let me get back to this slide. On the last thing I was talking about was now these results from Lauren and von Brecht on the filling architecture case, which is an immediate corollary from the proposition above, and in not as immediate, but kind of, now I cannot change my slides, now I can, okay. It's also this result that is at least due to Baldi and Hornig from 89, and then reproven by Kawaguchi in 16, that if I am working with a quadratic loss small l, then also it is true that there is no bad minima. And this is not as immediate, but I want to tell you how you see this as a corollary from the proposition above. And what the geometric meaning behind this is. And so the strongest part of this statement of Kawaguchi is that, and Baldi and Hornig, is that this is true even in the non-filling case. So where our neuromanifold is not a vector space anymore, it is in fact a determinantal variety, this nice algebraic variety of matrices of bounded rank. Okay, so to tell you how you see this result, let me recap what the quadratic loss is. And then let me tell you how I like to think about it, being not a machine learner, but being an algebraic geometer. So I have fixed data matrices X and Y, and then the quadratic loss is often written like this, like the capital F at the norm means I'm working with the Frobenius norm of matrices. Okay, and now let me make a very easy observation. This is something that you can work out on paper right now if you want, or after the talk. It's very easy to see. If we assume for a second that XX transpose is the identity, this assumption is sometimes called whitened data, then I can rewrite the loss function. And essentially what happened is I moved X from one side to the other, and then I add some constant terms. Constant means it does not depend on the capital M. And another thing, 2 things I want to add here. So first of all, I could have also assumed that XX transpose is invertible. Then it's a little bit more technical what you want to write here, but essentially the same thing is true. So you don't need the identity. You just want that XX transpose is invertible. And this is also a common assumption you sometimes see. And that is, I think, the reason. The underlying reason is because then you can rewrite the loss is actually, you can rewrite it in this shape. And why is this nice? It kind of looks the same, but the meaning changed a little bit. So the important takeaway message is that minimizing the quadratic loss on the determinantal variety of matrices of bounded rank is actually equivalent to minimizing the standard Euclidean distance of the fixed matrix YX transpose to the determinantal variety. So this is somehow two very related problems that are equivalent in the sense that since I minimize them and they only differ by constant factors. So if I want to understand this result by Kawaguchi, and I'm happy with making this assumption that XX transpose is invertible, then I'm fine with studying the Euclidean distance problem of a fixed matrix to an algebraic variety. And this is a classical problem in differential geometry and algebraic geometry for a long time, and is also very popular, I think, in modern applied algebraic geometry these days. So let me tell you a little bit about the general setting and how I like to think of these neuromanifolds in this setting. So for any algebraic variety, I know for many algebraic varieties it's a scary word, but I claim it's an easier concept than a manifold. So if you know manifolds, don't be afraid of varieties. And variety for us right now is really just you have some set of polynomials and you want to study their common zero locus. Well, it's just like linear algebra where you work with linear equations, but now I work with polynomials. So I do nonlinear algebra. Okay, here is an important well-known theorem in algebraic geometry, which is very, very strong and might be surprising on first sight. So there is some sort of number, a constant, such that for almost all points, this could be data points, think of them as data, the data matrix. The minimization problem of finding the closest point on the variety Z to this data point Q, this has exactly delta many complex critical points. So this seems like a big thing, so let me make an example. This number, by the way, is called the Euclidean distance degree. And here is my first example. So if your variety is a circle, then I claim this number is 2. Right, so here's an example. There was like a point that I marked, a white point. And so that I want to solve the problem to find the closest point to the given point on the circle. Okay, so if you try to solve this problem and you aim to compute its critical points first and then decide which one is the minimum afterwards, then you see the answer is 2. There is actually the closest point and then the furthest away point. Does that make sense? So that answer is 2. Slightly more complicated example is an ellipse. So here is a picture of an ellipse, which has this number is 4. So I marked it an example here. If we consider this point that I now try to make bigger in yellow, then I can plot for you what the 4 critical points are on the ellipse. Then this one, I can only plot 2 points for you that are critical points, because there is 2 more, but they are a complex conjugated pair. So I can't really see them right now. But you can believe me, and you can make the computation that also this other point, which only seems to have 2 critical points, actually has 4 of the complex numbers. And it is true that whenever you pick a random point on the plane, it's going to have 4 critical points. The points where you do not have the correct number, like 4 in the case of the ellipse, these exist, and they are going to form some sort of complex hypersurface called the discriminant of the variety. And in these examples, the discriminant is exactly this diamond shape. So when you pick a point, say here on this orange boundary, that point would have 3 critical points. And then something more crazy happens at these vertices of the diamond, but I don't remember the numbers right now on the top of my head. But everywhere else, you're going to have 4 critical points. And for the circle, like the circle is for me really a degeneration of an ellipse, right? So this funny orange discriminant locus is really just the origin, right? Because at the origin, I in fact have infinitely many critical points. Like every point has the same distance, of course. So, and that's why this is the only point where I do not have 2 critical points. And I am showing you these pictures because I somehow want to advocate that when I have a linear network and its neuromanifold is these rank-bounded matrices, then these neuromanifolds, they are kind of like circles. They have more the behavior of circles. My pen is doing weird things, I'm sorry. Than the behavior of an ellipse. So let me apply this and let me motivate this a little bit more formally. So from the algebraic point of view, let me formulate the well-known Eckert-Young theorem for determinantal varieties, which are our neuromanifolds. So first of all, whenever you have a data matrix Q and it's somehow random, here is also very specific what it means. Full rank with pairwise distinct singular values. This is always going to be true when you pick a random matrix, like with probability 1. Then this optimization problem, finding the closest point on the determinantal variety to Q, we know how many complex critical points it has. That's the Eckert-Young theorem. It's this nice, beautiful binomial coefficient. So this coefficient is exactly this Euclidean distance degree of the neuromanifold. There is more parts that I would consider somehow a summary of Eckert-Young theorem, which is that all these critical points are in fact real. And that gives you a first hint that these determinantal varieties look like circles. Because it in fact means that this ED discriminant is not a hypersurface over the real numbers. It really has codimension 2, as in the circle picture, right? If you remember, it was something like there was the circle. I'm better drawing circles. And then there was an orange origin, which I now have read here because that's a story I have, color I have easy access to. Okay. Okay, so ED discriminant is also of codimension 2 in the circle case, as it is for these determinantal varieties. In fact, you can also see what it is. Matrices with coinciding singular values. And moreover, third part of Eckert-Young is that this minimization problem has a unique local and global minimum, which is really somehow the key property from the machine learning perspective somehow, because that just exactly now gives us a geometric proof just using other well-known results from way before, from the result by Baldi and Hornig and Kawaguchi, that if L is a small L is a quadratic loss, then I have no bad minima. Okay, so my time is kind of up, so I will just wrap up by telling you that linear networks can have bad local minima. So the statement that they often have it, if you consider that statement wrong or false, really depends on your perspective. From my perspective as an algebraic geometer, I would say the statement is false. And so why would I say that? Because whenever I have an algebraic variety like the circle or the neuromanifold of a linear network, then if I would perturb for instance, the variety a little bit, and then compute the ED degree. This is what's happening in this sentence. So there's a constant delta gen, such that whenever I have like a random linear coordinate change, which I perturb my variety, and then the ED degree is this new number called the generic ED degree. And this is an interesting number because what happens if you start from a circle and you perturb it randomly with linear coordinate change, you get an ellipse. Right? So there's the connection. So the ED degree of a circle is 2, but its generic ED degree is 4. And that is one way of thinking about a problem. And more relevant to machine learning, I think, is this other way of thinking about the problem of you could fix your variety, of course, and instead use a different distance measure. And that is the same thing as fixing linear networks, fixing their neuromanifolds, but then changing the loss function a little bit. Not have anymore the standard quadratic loss, but have a perturbed version of Euclidean distance. And then the whole story changes drastically. It's not just the number of critical points that changes from the algebraic geometry perspective. It is the whole geometry of the optimization problem. In particular, there will be bad minima whenever you do that. So in fact, for almost every perturbation of the quadratic loss, you will have bad minima. So I'm just showing you one example where we did some specific study. So for instance, if you work with a network that looks like this, you have here input and output size 3, and then you have 1 in the middle or something. Or you can have possibly more layers, but at least one layer of size 1. So this will be 3 by 3 matrices of rank 1. Then it has 3 critical points, but under this perturbation to a different loss, you get 39, much larger number. Also, this ED discriminant is now actually becoming a hypersurface of the real number. So it's like in the circle case, where in the circle I started from a picture like this, and then when I do the ellipse, I end up with a picture like this, which means that you have different numbers of real critical points in different regions of your ambient space. So it depends on the data matrix how many real critical points you get. But in the Kathlen theorem situation, critical points, all of them were always real. This is not true anymore if you perturb the quadratic loss. And you have bad minima and a different number of local minima. And we made some sort of experiments. You can look at the paper if you want. And I wish I could give more details than just experiments, but I think this is very hard questions to say something about the average number of local minima. So I think it's a very difficult problem. And this was not just an example. You can study that these neuromanifolds behave like this in general. Yes, and now I want to close with showing you just how crazy the world actually is. For these neuromanifolds, state of the art is we do not know a closed formula to compute the number of critical points. I only know this for rank 1 matrices. I know this beautiful formula, which is much more complicated. So this complicated formula was for the perturbed quadratic loss, and the easy formula for the unperturbed quadratic loss, which is just like a Young theorem. So there's lots of stuff to do from the algebraic perspective. And with that, I want to stop. So I'm not sure. Maybe I was on time.